speaker this afternoon is Kirsten Dickergren from Stanford, and she will speak on obstruction for homotopy sections for curves over nanofields. That's right.
Thank you. And we're going to talk about obstructions of Jordan-Ellenberg to homotopy sections. All right. And these homotopy sections are the same sections of the map on a tall pi 1 that Professor Zimweli was explaining yesterday. So the setup is that we take K, a subfield of C, and we're going to introduce the notation that G is the absolute Galois group of K. And we'll take a smooth curve, geometrically connected, curve over K. And then, as in yesterday, we have the homotopy exact sequence between the étal pi 1 of the base change to the algebraic closure and the étal pi 1 of the curve and the absolute Galois group. And so what we mean by a homotopy section is a section of the map on a tall pi 1. So a homotopy section of the structure map X to spec K, or let's say the homotopy sections. The homotopy sections are these sections of pi 1 X G up to conjugation by pi 1 X K bar. And the reason for the name comes from the fact that the non-abelian conjectures say that for K a number field and X a hyperbolic curve, that X should be equivalent to its pi 1. And we have the following basic construction. So if we had G prime any group, we're just going to let G prime be another group to avoid classifying spaces of profinite groups. So the reason for the name, this is reason for the name, is that if G prime is a group acting on the underlying topological space of X, and we'll say the Euler characteristic is less than 0, so it's topologically controlled by its fundamental group. Then if we formed the associated fibration of E G prime crossover G prime with X and C to B G prime, then here, this is a contractible space with a free action of G prime. So E G prime is a contractible space with a free action of G prime. Then the splittings of the pi 1 sequence are the same thing as sections up to homotopy. So then we have that sections of pi 1 E G prime crossover G prime X and C to B G prime up to conjugation are the same thing as sections of this map P. Well, only sections up to homotopy are the same thing as maps F from BG prime to EG prime crossover G prime X and C such that FP is homotopic to the identity and up to homotopy. And we have this picture of the Unabelian conjectures, which says that this is a good stand-in for X. It says that X should just be its fundamental group, should just be, this space has the fundamental group given by the same extension, the short exact homotopy extension. So we have this picture of the Unabelian conjectures. Which is saying that X, which is this total space of the fibration over BG, whose fiber looks like XK bar. And this is some sort of completion of the topological space we're used to thinking of as associated with the complex points, the analytic space of complex points. So this is supposed to be an analog for E, G, cross over G with X and C. So we're going to describe obstructions of Jordan-Ellenberg's two homotopy sections. And so there'll also be obstructions to rational points. And because we'll be able to draw these in small enough cases, we're going to give one more equivalent topological interpretation. So the last equivalent topological interpretation of this sort of sections of, well, I'm sorry, this is pi 1 and this is G prime. So sections of just the map on pi 1 of the fibration, or sections of the map on pi 1 from X to the Galois group, it's sections up to homotopy of these corresponding topological spaces. And equivalently, it's also a fixed point, or fixed points up to homotopy. So the last just reinterpretation of the topological analogy is that this set of sections up to homotopy is the same thing as if you take functions from this contractible space, so it's like functions from a point to X and C that are fixed under G prime. So if this were a point, this would just be the fixed points. But instead, it's this contractible space mapping here, and you're requiring them to be G prime equivariant. So these are the homotopy fixed point set, and we take pi 0 of this. And so in this language, the section conjecture says that the sections are the homotopy sections, or the fixed points are the homotopy fixed points. There's a natural map from fixed points to homotopy fixed points, from sections to homotopy sections, and that's supposed to be an equivalence. So the nice thing about having these as fixed points is that in some cases there are real theorems equating fixed points and homotopy fixed points. And so then we'll draw a picture of Ellenberg's obstructions in a second, where everything is easy to draw. So here are Ellenberg's obstructions. So we assume that X has a K point or tangential point B, and we're going to base all pi 1s at B. And we have one more piece of notation. So we had G is just going to be the absolute Galois group of K. And we're going to also just say that pi is the étal pi 1 based at B of xk bar. So it's an arbitrary piece of notation, but that's what pi is. And then since we have this rational base point, we automatically have a splitting of the homotopy exact sequence. So star becomes 1 pi the semi-direct product. And the homotopy sections, so these homotopy sections were the sections of pi g g up to conjugation, and this is now an H1 of g pi. And so we're going to study these. We're going to write down Jordan-Ellenberg's obstructions to these. And these use nilpotent approximations of pi. They use the lower central series of pi. So Ellenberg's obstructions. We filter pi by the lower central series. And this lower central series, just for short. So we have pi contains pi 2, pi 3, and this is more notation. And the definition of the lower central series is this closure of, so pi 2 is the closure of the commutators, and then pi n plus 1 is the closure of taking all the commutators with the last element of the lower central series. And we're going to approximate these homotopy sections that we want to study. By the image of pi over pi n of the, so we're going to approximate the homotopy sections by h1 of g pi over pi n. And for each n, we have a central extension giving the difference between the nth approximation and the n plus first, and that's the boundary map is Ellenberg's obstruction. So for each n, we have a central extension giving the difference between the two different terms of the lower central series. So pi over pi n plus 1 to pi over pi n to 1, and giving a short exact sequence of sets, giving the difference between our approximation, our nth approximation and our nth plus first, g pi n plus 1, h1 g pi n, and then this delta n map identifies which of these elements could actually have come from the n plus first approximation. And this goes to h2 g pi n plus 1. And this is the set of obstructions we'll talk about. So the picture is that these could be thought of as certain approximating space. So the picture without an example is that we have, by the non-abelian conjectures, that x is supposed to be b of pi 1 étal of x, which isn't pi. It's an extension of g by pi. And then we have the Jacobian of x is approximated by b of pi 1 étal. So here's a picture, étal of the abelianization, or of the Jacobian. We'll say x abelianized. And then above this, we stick the classifying space of pi and g, all in the tower. And in order to be able to draw, so we're making approximations to the curve with approximations to the fundamental group. And to be able to actually draw a picture, what we'll do is we'll say we approximate x g equivariantly, or approximate x k bar g equivariantly by the tower b pi abelian b pi over pi 3, etc. And the example, we'll take P1 minus 3 points over R, and we'll draw B pi ab, B pi 3, and we'll show the homotopy sections, and we'll show what the obstructions do to each one. So we're going to draw this picture in the case P1 over R minus 3 points. So we'll use a tangential base point at 0 pointing towards 1. And the algebraic closure of R is C, so it looks like a sphere. So example, x equals P1 R minus 0, 1, infinity. And we have 0, 1, infinity, and here's the P1R inside there, the fixed points. And here's the base point we're going to use. And the fundamental group is the profinite completion of two loops, alpha 1, and alpha 2. And so this, since taking out these little points, you can contract back onto these loops. This is a nice classifying space of pi. So that's our space here. And then to form the classifying space of the abelianization, we have the abelianization has one axis for alpha 1 and one axis for alpha 2. And you glue up by adding alpha 1 and alpha 2. And you get the 2 torus. And the GR action flips the alpha 1 and alpha 2. So the fixed points are the 4 2 torsion points. Now, if we want to do the classifying space of the triple commutators, we also get of the 2 nilpotent quotient. We have an axis for alpha 1, we have an axis for alpha 2, and we also have a non-trivial commutator. And you can check that a classifying space for this, you glue up a cube, and you can choose a model so that you glue the front to the back, and you glue the top to the bottom because it's in the center. But one side gets glued to the other by a shear. And so you glue this left-hand side to the right-hand side by shifting up and gluing. So what happens? Well, the fixed points here, we have one fixed point for the intersection of this loop with P1, one fixed point for the intersection of this loop with alpha 2. This goes to here, this goes to here, and this goes to here. And then when you try to lift these fixed points, you do get a lift here of this point, you get a lift here of this point, and you get a lift here, but there's no lift of the center. So delta 2 has gotten rid of the extra point. We had 3 points of the curve going into 4 of the Jacobian, and 3 of them lifted, the 3 from the curve, but the last one was picked out by delta 2. And it's a fact that for p groups, fixed points and homotopy fixed points are the same. And so delta 2 is exactly determining the homotopy sections here, and this turns out to be typical. So it's a fact that over R, delta 2. Yes, please.
So here, because it's homotopy, you somehow has common components.
Exactly. Yeah. It's pi naught of the fixed. So when we say that the fixed points and the map from fixed points to homotopy fixed points is an equivalence after certain sorts of completion by Sullivan's conjecture for p groups, and a weak equivalence, and then the map on pi 0 is this bijection that you can rephrase the section conjecture in terms of when people talk about the section conjecture over R, they don't mean the R points, they mean the connected components. And Ellenberg's obstruction over R does always pick out the connected components of real points of the curve from those of the Jacobian exactly. So we have the following. And in the above example, x wasn't proper, and it's not that I don't believe this is true for x non-proper, but this is what I can show at the moment. So for x over spec r, smooth, proper, genus greater than or equal to 2. Then the kernel of delta 2 is precisely the homotopy fixed points of the curve. Is precisely the homotopy sections of the curve. Then kernel of delta 2 is equal to h1 g pi injects into h1 of the pi abelianized, and we have equivalences between fixed points and homotopy fixed points that we won't go into. So in other words, if you want to recover these connected components of real points of the curve, what you do to the Jacobian is you add fibers corresponding to the 2 nilpotent quotient of the fundamental group.
So you're assuming the x and the
Yes, I'm sorry. So a little about the structure of delta n. So
when you write kernel delta 2 is that thing.
it's the image of that
Image
thing.
of it.
And in fact, that thing injects into, in this case, it means the image, and this image is, so image, and then this one is an injection. A little on the structure of delta n. And, no, we're going to view the delta 2 as a function on the homotopy points of the Jacobian. So what we're doing is we're making an obstruction on the homotopy sections of the Jacobian, and the kernel of that is this image of the points of the curve. We know some things about the structure of the delta n. So the delta n and are related to Massey products. And so Ellenberg showed that delta 2 is a linear perturbation of a cup product, or a certain cup product composed with a commutator. So proposition for any x in the homotopy sections of the Jacobian then delta 2 is equal to the cup product of x cross x pushed forward by a commutator and times 1/2 plus a term which is a homomorphism. So where this commutator is the map from the abelianization pi 2 tensor pi 2 pi 2 over pi 3 is the commutator. So of gamma 1, gamma 2 is equal to gamma 1, gamma 2, gamma 1 minus 1, gamma 2 minus 1. And L is a homomorphism. Is linear, is a homomorphism.
So the Heisenberg groups sort of is sort of related to the things in Manfred's lectures on the
I'm sorry, what was the question? The Heisenberg
These sort of
group?
Heisenberg type groups.
That's right.
Are they related to the ones in Manfred's lectures on the
I'm not sure in,
Yeah, it's Heisenberg.
all right,
Yes, it's
thanks.
equal to torus S1 over torus.
That's
S2,
absolutely,
which
yes.
corresponds to
Yeah.
non-trivial H2.
Yeah. So one way that this can be shown is by manipulating cocycles, and instead we'll proceed by slightly separating the very concrete, boring topology of the curve from the incredibly interesting Galois action, and by slightly separating the two, we'll be able to generalize this decomposition. And so we'll need a little more notation to say it, but the first approximation of this structural fact about delta n, so approximation of the theorem, is under hypotheses. And this is, think small n. X has to have at least one puncture because we are going to use the fact that it's a free group, and the proof uses that necessarily. X has at least one puncture. Then delta n decomposes as a term which we'll call bracket Massey product of order n. Plus a term that's subject to a weak form of linearity, where L satisfies L of x plus y, but since these are going to be non-abelian groups, this only happens when x, y can be put together so that the corresponding cocycle is another cocycle. For instance, the indeterminacy of the lift from the next stage is where one's in the center of the other. So this is a lousy definition when x plus y admit a sum, but nonetheless we're going to pull off a piece that looks higher order than the remainder. So it satisfies the fact that L of x plus y is equal to L of x plus L of y when x and y admit a sum. And remark, this piece requires knowing less about the action. than you'd expect. So remark 1, computing delta n requires understanding a larger piece of G's action on the nilpotent completion of pi, requires understanding how G acts on pi n plus 1, but the bracket Massey product term requires one less piece. And the hypotheses, remark 2, to form an order n Massey product, you need vanishing of order n minus 1. And approximately what's going on in the hypotheses is that to have the vanishing of the lower order ones, you need the lower order delta n's to be the Massey products. So you get a decomposition until the linear term doesn't vanish. So hypotheses are approximately that delta m of x is equal to x m for all n less than n, but they're stronger than this in a way that will become clear with a little more notation, but stronger. To be precise, but also to do a little towards separating the curve from the action, we're going to need a little more notation. So we're going to let omega n be the class of the extension associated to the difference between the n plus first approximation and the nth approximation. So let omega n in H2 is pi n semi-direct G pi n plus 1 being the element classifying the extension 1 pi n plus 1 pi over pi n plus 1 semi-direct G pi over pi n semi-direct G1. And recall that this class is associated to that boundary map in group cohomology in the following way. So if you take a homotopy section, this is a map up to homotopy, and choosing a cocycle is like choosing a map. And so and this can also be expressed in terms of homomorphisms of groups or homomorphisms of groups up to conjugation. So we're going to let the corresponding map of a homotopy section, so H1G pi n determines a map up to conjugation, but we'll pick a cocycle. This is a representing cocycle. And then the way boundary maps in group cohomology work is just that the boundary of X is equal to the pullback of the class classifying the extension. And so we'll relate the spectral sequence decomposition of a semi-direct product with the filtration corresponding to a spectral sequence corresponding to a semi-direct product with the linearity properties of the corresponding obstruction. And this result may be folklore. So we can form obstructions with elements of H2, and we can filter H2 via the spectral sequence corresponding to that picture of the curve, that complex curve over the absolute Galois group. So the H2 of pi n g that we can use to make obstructions is filtered by the spectral sequence corresponding to the extension just for this group, which is connected with our picture that the curve is this interesting fibration over the classifying space, corresponding to 1 pi n g to g, which looks like this. And and then the spectral sequence, it has, for the H2 term, it has an H2 of pi n fixed by g. It has an H1 g, H1 pi over pi n. And all the coefficients are all going to be in here, and they're twisted. And then we have H2 of g. And when you take the corresponding obstruction, if your element of H2 is in here, you get a linear obstruction in the limited sense over there. And if your element is in here, you get a constant obstruction. And so the highest order term is coming from a class which is in H2 pi over pi n, and which moreover we can calculate without any knowledge of the Galois action. So the proposition, which has nothing to do with that last piece of sentence I said, the proposition which just says elements of here correspond to constant obstructions, elements here correspond to this linearity type condition. So the proposition is that for any eta in H2, we can define an obstruction, pi n g. Let d of eta of x just be the pullback of the class eta. And then for eta, by the way, this spectral sequence, because of the existence of a rational point, it has splitting so that the filtration is actually this, and then the direct sum of this, and then the whole thing. So this picture, which is the E2 page, the filtration period is this inside this plus this, so we're going to abuse a little bit. So for eta in H2G, d eta is constant. For eta in H1G, H1 phi n, d eta, I'm going to put is linear, but in quotes, because this doesn't mean all we'd like it to mean. So why does this give a generalization of the structure of the delta n? So
Eta in H2 on.
So for then d eta is constant. So when you build an obstruction map from H1 to H2, and you build it with the principal obstruction, or the element classifying the short exact sequence up there, when that element lies in H2 of G, the corresponding obstruction is just constant. If that element lies in H1 G, H1. Here, that element is subject to a linearity condition.
And so could you maybe repair what you say in the proposition? For eta
So-
in H2 and so on, let
For eta in H2 of pi over pi n, semidirect G,
Yes.
and the coefficients are pi n
Yes.
over pi n plus 1.
Mhm.
Then we're going to take the corresponding obstruction. So this says let d eta x be the corresponding obstruction, and the corresponding obstruction is x actually corresponds to a map, or a map up to not enough conjugacy to mess up cohomology. So this is that map, and you pull back the class of eta. In other words, you're trying to lift through a fibration, and you know the principal obstruction to lifting through the fibration, and you're pulling back that principal obstruction to see if your section lifts to a section in the above space. And this eta would be the obstruction to the existence of a section of the whole fibration, not just lifting your section x to the bottom space to the top space. So corresponding to a class eta in H2, we have an obstruction map, and this obstruction map has linearity properties controlled by the Serre spectral sequence decomposition according to this vibration, that the piece coming from here is not controlled by a linearity property, but the piece is 0. So then this gives this.
Can I ask one more question?
Yes, please.
So you kind of explained why the linear is in quotes. Could you just say again?
So if you.
That object, that is an abelian group, or that's something else, the H1G?
No, the H1 is not. So this obstruction goes from H1 G pi pi n to H2 G pi n plus 1. And this is what d eta is. This is a homotopy section to this approximating space or group, if you like. And we're seeing which ones lift to the next approximating space. And to do that, you pull back the principal obstruction. And then from that, we get clarification of what hypotheses are, and we get this decomposition. And the reason for that is that this piece is just whatever class classifies the lower central series of free groups. So work of Dwyer can compute the piece of the obstruction in there, and then it's messy work to lift that back up to a class. But let's write down what we're doing. So let I be this inclusion of the kernel or the fiber, be this inclusion. And then I star of the class classifying that extension is just the class classifying an extension of free groups. So can be expressed in terms of Massey products using work of Dwyer, because this is now independent of the action. So I star omega n can be expressed with ordinary Massey products. You know, none of these extra commutators sticking out in front can be expressed with Massey products by work of Dwyer. With bracket Massey products, we can find with bracket Massey products, or a bracket Massey product, exists in H1 pi n G pi n plus 1 over the Massey product over I star omega n. And I want to say one thing about what bracket Massey products are. So Massey product uses an associativity of the cup product to make these higher operations. So Massey products use associativity of cup product to form higher cohomology operations. And bracket Massey products are an imitation of the Campbell-Hausdorff formula. Bracket Massey products are an imitation of the Campbell-Hausdorff formula that allow us to replace this associativity with the Jacobi identity on pi n, allowing us to replace associativity with the Jacobi identity, allowing associativity of cup to be replaced by Jacobi identity on pi n over pi n plus 1. And the hypothesis that pi is free is necessary to make that work. And this gives the theorem and the hypotheses. The hypothesis is that the bracket Massey product is the classification of the extension, of the previous extensions. And then, so it's a sort of inductive process. If you get your first, the structure of delta 2, if the linear term vanishes, you get a structure of delta 3. If that next linear term vanishes, but what we mean by the linear term vanishing is the associated cohomology class vanishes, which is a little stronger. If that next linear term vanishes, you go on up. And so we'll now see what can be computed for x equals p1 minus 3 points. So that that's the end of this piece of structure of delta n. So the next thing is we'll take x equal to... Yeah.
So what you were explaining here is the ideal how you prove the theorem?
Right, combined with the hypothesis, which is basically that you get a decomposition until the linear term doesn't vanish.
Right.
But since what's meant by the linear term vanishing isn't the map vanishing, which is what should be meant by it, but which is with the associated cohomology class vanishing, it's also sort of in the statement of the theorem. So that gives the decomposition and the hypotheses. So for x, for x equals p1q minus 0, 1, infinity, we do have the first linear term vanishing, and delta 3 gets decomposed into a Massey product term and a lower order term. And so we'll use the same rational base point as in the picture example. So we again have P1Q, and we have 0, 0, 1, infinity. And we use this rational base point. The linear term changes with the change of rational base point by cupping with the difference of the two products. And we have again that that pi 1 is these two classes, alpha 1 and alpha 2. And Ellenberg noticed that the the linear term of delta 2 vanishes. So delta 2 of x is just the bracket cup product, 1/2 after inverting 2. X cup x. And the Jacobian of x is 2 copies of GM for how you glue together a line bundle at the points that you glue. So the Jacobian of x is equal to GM cross GM. And then the 2 projections means that you can decompose a homotopy section into of the Jacobian until it's this GM coordinate and this GM coordinate. So we have GM, GM. These 2 projections means that we can decompose x in H1 G pi 2 as x is equal to the coordinate on the first GM, direct sum the coordinate on the second GM, where xi is in H1 G C hat 1. And the action on P1 minus 3 points is well known to have the following form. For instance, it's in the Drinfeld's Grothendieck-Teichmuller group definition. So G acts on alpha 1, alpha 2 in this manner. Sigma acts on alpha 1 by raising alpha 1 to the cyclotomic character, and sigma acts on alpha 2 via a mysterious cocycle, which we'll call F. So we have F minus 1 of sigma, alpha 2, chi sigma, F sigma, and chi G C hat 1 is the cyclotomic character. And F G 2, it's in the commutator group, is a cocycle. And so then we can figure out what the third obstruction is, and it looks like this. It's got Massey product terms out in front, and you can break it up into 2 different obstructions corresponding to the 2 different commutators. We have, we could take alpha 1, alpha 2 commuted and then commute with alpha 1, or we could take alpha 1, alpha 2 commuted and then commute with alpha 2. And this breaks up delta 3, and then we can compute both. So pi 3 over pi 4 has this decomposition into 2 copies of Z3. And this means that delta 3 is actually 2 obstructions. So delta 3 is equal to the obstruction corresponding to one commutator, direct sum the obstruction corresponding to the other one. And then we have that delta 3 of the commutator with the 2 alpha 1s is a Massey product with the 2 x1s, x2, x1, x1, plus a Massey product with the cyclotomic character minus 1 over 2, x1, x2. And the delta 3 with the commutator with two x2s has an extra term involving cupping with f. It's the Massey product it has to be, except because of choices of bases, they're funny signs and things aren't exactly symmetrical, but x1, the Massey product x1, x2, x2, plus the Massey product chi minus 1 over 2, x1, x2, and then it's minus a cup product of this cocycle and x2. And the choice of lift from the Jacobian to the 2-nil approximation is encoded in the defining system of this Massey product. So the cycle whose boundary is this is the cycle telling you which lift you are to the 2-nil approximation. So we'd like to evaluate these as 0 or non-zero. And so as they've been given now, that involves evaluating a class in H2 with coefficients in z hat twisted by 3. And instead of working there, we'll work in the Brouwer group by taking a quotient to z mod 2, so that z mod 2 twisted by 3 is z mod 2 twisted by 1, and so that we can compute in the Brouwer group. And we'll also compute locally, so that the Brouwer group is just this z mod, well, the 2 torsion in the Brouwer group, which is where will be a z mod 2. So to evaluate delta 3,
Can I just ask, is the
Yes.
f cup x2, is that an example of an L?
that's an example of an L. Yeah, with actually the L includes the chi minus 1 over 2 x1, x2. It doesn't look like an L, but that's because what L means is funny. But it's lower order because there are sort of 3 x pieces in the first piece, and then and so we're going to change the delta n definition to work in the Brouwer group. So to evaluate delta 3 as 0 or non-zero, we'll replace the lower central series by the exponent 2 lower central series. And so the definition of that is that you take as pi n plus 1, you take the closure of pi with pi n, but then you take all these brackets, but then you also kill anything in pi n squared. And to avoid using the same notation for the lower central series and the lower exponent 2 central series, we can add a 2 up here, but that's not as a squared. So that's what the exponent 2 lower central series is. And then this means that our obstructions lie, so image of delta 3. Oh, and then we'll restrict.
Wait, sorry, you're saying we're killing anything there?
We're killing anything in the square of the one below. So
Okay,
the
so
successive quotients
so
are
it's not
always.
That, okay.
It's so right. So this is the exponent 2 lower central series are
Okay,
these
right.
things, and then we form the obstructions with the corresponding pi over pi ends.
This one we
And
graded factors are all of two elementary.
that's right. And they're Z mod 2 vector spaces,
No.
or maybe that's the same. And then we'll restrict to QP, and we're going to assume P is congruent to 1 mod 4. Restrict to QP with P congruent to 1 mod 4, and then the image of delta form corresponding obstructions. And then the image of delta 3 is now just in this Brouwer group. G QP C mod 2. And then we can evaluate delta 3 on an infinite subset of the points of the Jacobian, but they're all under restrictive enough hypotheses to make the Massey products computable with cup products. So they're in, we can evaluate delta 3 on infinitely many points of the Jacobian, but it's by putting on a lot of conditions. So for take A, B, in Z cross C in GM Q cross GM Q is equal to the Jacobian, the Q points of the Jacobian, and we suppose that P divides AB exactly once, and then it's just a standard cup product calculation. That gives you what when delta 2 vanishes. It vanishes when their sum is a square mod P. Standard cup product calculation implies that delta 2 of AB is equal to 0 if and only if A plus B is a square mod P. And then it takes more work to say that you can delta 3 of AB, by which we mean there exists a lift of this point of the Jacobian to the nilpotent, to the two nilpotent group equals 0. And in fact, you can identify the specific lifts and evaluate explicitly on each one. But in this form, we have that delta 3 of AB is equal to 0 if and only if A plus B is a fourth power mod P. And that's it.
Thank you. Are there questions?
Yeah, I mean, sort of a vague question, but I mean, the thing I would have sort of thing I was looking at. I mean, if you replaced the, you know, you're doing non-abelian cohomology, so somehow you replace that by the group ring, something like that, and you replaced your lower central series by the, you know, the augmentation filtration. I mean, that allows you to extend your sequence. I mean, does this tell you anything?
You want to replace a cohomology group by the group ring? Is that a piece of intuition? I don't know an intuition that allows you to replace a
Well, I don't know that
cohomology
it would
group
give you
by
all the same thing. It might give you something interesting.
I haven't thought about using a group ring as a way to approximate sections or points.
We say delta 3, no, but this delta 3 is really then delta 3 in the new setting, yes.
So this is, we could say, we could restrict and we could form the corresponding obstructions and we could call them delta 3 2P,
but then
and then this would be better.
2 also, and also in the proposition.
Yeah. And this means there is a lift. And in fact, you can do better. You can identify the lift specifically and evaluate the obstructions explicitly on each lift with more work.
A plus B is a fourth power means something about the set.
Fourth power mod P.
What is means something about
It's trying to be 1. It means that this Abel Jacobi map is this. Yeah, yeah. Yeah.
Ideally, it would be if you not work modulo 2, you will get A plus B is 1, I think.
Only if the lower central series is a good enough approximation for that. I mean, that's an interesting question. Like, how well does the lower central series really approximate the curve?
So that's going to be another question. Is there
That's
a yoga
right.
for that?
No, I mean, it looks a little like what would be captured by the Z completion, what would be captured by I don't, I'm not confident about the following statement, but it's a little like stabilizing and then unstabilizing, and then you lose anything but the nilpotent completion. And so why should that be as good as the curve? Maybe if you have a better intuition than the fact that some sort of nilpotent completion is like taking the spectrum and then going back to the space level, that's, I could definitely believe there's better intuition out there. It's a little like that.
So I had one quick comment about Romeo's question. That if you're interested in classes of points, you don't get H1 classes in group rings at all. It doesn't naturally live there at all. It only lives naturally in non-abelian homology.
So the
Actually, you work modulo with 2 and modulo 2 and so on, because new topologies are somehow ahead of us, but we can do constructions only because it's 2 comes from topology.
No, that's much too nice. 2 is just 2 twisted by 3 is the same thing as Z mod 2, so you can do it with Z mod 3, and that's it. It's because you don't want to wind up in Z hat twisted by 3, because I don't know how to compute in there. And so if you want Z hat twisted.
Potentially, you could do this for, modulo M, and maybe not modulo. But
If you could handle the cohomology group of Z mod N twisted by 3 in a computational fashion.